Every telescope humanity has ever built, from Galileo's simple handheld lens to the James Webb Space Telescope, currently sitting nearly 1 million miles from Earth, has given us the exact same fundamental thing: a snapshot. A single frozen moment captured once, studied carefully, and then set aside as astronomers move on to point their instruments somewhere else. Yusra Al-Sayed, the Princeton researcher overseeing image processing for a brand new observatory in Chile, put the limitation of that entire approach in blunt terms. A snapshot, however detailed, simply doesn't tell you the whole story of a universe that never stops changing. On June 23, 2025, that 400-year pattern in astronomy quietly ended. Because the telescope that released its first images that day wasn't built to take one more beautiful photograph of the night sky. It was built to do something no instrument in the history of astronomy has ever attempted: photograph the entire visible sky, over and over, every 3 nights, continuously for an entire decade, transforming astronomy from a collection of still photographs into something closer to a movie. This is the real story of what the Vera C. Rubin Observatory actually is, why its first images represent far more than a single stunning reveal, and why the true significance of this telescope won't be fully understood until years from now. I'm your host, and this is your channel. If you want the real science behind the biggest ideas in space, subscribe now, because we're just getting started. To understand why Rubin represents something genuinely different from every telescope that came before it, you have to start with a basic, almost embarrassingly simple problem that has quietly limited astronomy for its entire history. The universe doesn't sit still. Stars explode. Asteroids drift across the sky at night. Distant galaxies flicker with brief, violent bursts of energy from black holes tearing apart nearby stars. And for centuries, the fundamental way astronomers studied the sky involved carefully selecting a single target, pointing a telescope at it, and capturing the clearest, most detailed single image possible. That approach works beautifully for studying something that holds still, a distant, unchanging galaxy, a stable nebula, a planet with a predictable orbit. It works far less well for studying a universe that is, in reality, constantly in motion, full of events that flare up and fade away over hours, days, or weeks, often in parts of the sky nobody happened to be looking at when they occurred. The Vera C. Rubin Observatory, sitting atop Cerro Pachon in the Chilean Andes at an elevation of roughly 5,200 feet, was specifically engineered to solve that exact problem. At its core is the Simony Survey Telescope, an 8.4-meter mirror paired with the LSST camera, the largest digital camera ever constructed for astronomy, roughly the size of a small car and capable of capturing 3,200 megapixels in a single exposure. But the camera's raw resolution, as genuinely impressive as it is, isn't actually the most important thing about this observatory. What matters more is speed and repetition. Rubin is specifically designed to scan the entire visible portion of the southern hemisphere's night sky roughly once every 3 nights, systematically, continuously, without pause, for 10 straight years, as part of a formal dedicated survey called the Legacy Survey of Space and Time. Sarah Benito, a member of the board of directors for the LSST Discovery Alliance, explained exactly what that continuous, repeated scanning actually makes possible, in terms that get at the heart of why this telescope matters so much. If something in the sky moves or changes, she explained, Rubin will detect it and distribute that information to the entire world in real time. That capability, she noted, means astronomers will finally be able to observe genuinely transient phenomena as they actually happen, opening the door to new, often completely unexpected astrophysical discoveries that simply weren't possible under the old snapshot-based approach to astronomy. Benito described the ultimate result of this decade-long project in a phrase that captures the shift better than almost any technical explanation could. Rubin, she said, will produce a true multicolored movie of the sky lasting an entire decade. That reframing from static photograph to continuous movie is exactly why Rubin's first images, released to the public on June 23, 2025, mattered so much more than their surface-level beauty alone. One striking early mosaic combined 678 separate exposures, gathered over a little more than 7 hours of total observing time, revealing faint, glowing clouds of gas and dust belonging to both the Trifid Nebula and the Lagoon Nebula in remarkable detail. A second image, quickly nicknamed the Cosmic Treasure Chest by the astronomical community, captured the southern Virgo cluster, the closest large galaxy cluster to our own Milky Way, containing millions of individually resolved stars and galaxies, spiral arms stretching lazily across the frame, galaxies caught mid-collision, faint filaments tracing out the larger cosmic web connecting distant clusters together. These weren't randomly selected targets, chosen simply because they'd photograph well. Alan Rudman, one of the observatory's senior scientists, made an almost startling admission about that during a preview press conference. In a lot of ways, he said, it almost didn't matter where the team pointed the telescope. They could have aimed it at nearly any patch of sky and still produced genuinely fantastic images, a direct demonstration of the instrument's raw underlying sensitivity, entirely independent of which specific, camera-friendly target happened to be chosen for the public reveal. But the genuinely important test of Rubin's design didn't come from these carefully chosen, deliberately photogenic first images at all. It came from something far less visually dramatic, buried in the observatory's own preliminary test data. More than 2,000 previously unknown asteroids, identified in our own solar system, discovered during just 10 total hours of early test observations, conducted while the telescope was still technically in its commissioning phase before its formal 10-year survey had even officially begun. That number matters enormously because it's a direct, concrete demonstration of exactly the kind of change detection capability Sarah Benito was describing, the ability to notice something moving, something new, something different, buried within an otherwise familiar patch of sky. Finding that many previously uncatalogued asteroids in just 10 hours, using an instrument still technically being calibrated and tested, offered a genuinely striking preview of what a full decade of continuous, systematic scanning is realistically capable of producing, not in some distant theoretical future, but immediately, right from the very beginning of the survey's operational life. It's worth understanding exactly what scientific questions this specific approach, repeated, continuous, whole sky scanning, rather than occasional, targeted deep observation, was actually designed to help answer, because the two primary goals behind Rubin's entire 10-year mission connect directly back to the telescope's own namesake. The observatory is named for Vera Rubin, the American astronomer whose painstaking, careful measurements of galaxy rotation speeds during the 1970s provided some of the earliest, most compelling observational evidence that dark matter, an invisible substance that appears to account for roughly 85% of all matter in the universe, genuinely exists, even though it cannot be directly seen or detected through any conventional means. Rubin's own namesake mission is now specifically designed to help finally reveal dark matter's true underlying structure, using a real, measurable physical effect called gravitational lensing. The subtle way light from extremely distant galaxies gets bent and distorted as it travels through the gravitational influence of matter, including invisible dark matter, positioned somewhere along its path toward Earth. Detecting and precisely mapping that lensing effect across truly enormous swaths of the observable sky requires exactly the kind of wide-field, statistically powerful, continuously repeated observation that Rubin, uniquely among current telescopes, was specifically engineered to provide, something a narrower, more traditionally focused telescope simply cannot accomplish at the same scale. The same underlying survey is also expected to make direct, meaningful contributions to understanding dark energy, the second half of the universe's two great modern mysteries, the mysterious force that appears to be driving the accelerating expansion of the universe itself, pushing distant galaxies apart from each other at an ever-increasing rate. Charting how galaxies and galaxy clusters are distributed across truly cosmic distances, and carefully tracking how that large-scale distribution shifts and evolves over Rubin's full 10 years of continuous repeated observation, is expected to give researchers one of their most statistically powerful tools yet for constraining and refining our current models of exactly how dark energy actually behaves. Reactions from working astronomers, once they'd had genuine time to absorb what Rubin's approach actually represented, consistently returned to this same underlying theme, the shift from static image to continuous, evolving record. Meg Schwamb, an astronomer at Queen's University Belfast, described June 23, 2025, as the true dawn of the Rubin Observatory, explaining that for the entire preceding decade of construction, everything about the telescope's promised capabilities had existed purely in the abstract, discussed in research proposals and technical specifications, rather than demonstrated through actual working data. On that specific day, she said, that long-standing promise finally became a real, functioning reality. Catherine Haymans, the University of Edinburgh astronomer who holds the formal title of Astronomer Royal for Scotland, echoed a similar sentiment, telling the journal Nature that she felt the entire astronomical community had genuinely been preparing for this specific moment for years, anticipating the start of a 10-year mission that had, until that day, existed only as a plan on paper. So here's where this genuinely leaves things, honestly, based on exactly what astronomers themselves have said about this telescope's true significance. Rubin's first images were beautiful, and they deserved every bit of the immediate public attention and admiration they received. But the deeper, more important story here was never really about any single image at all. It's about the fundamental shift in how astronomy itself now works, the transition away from centuries of collecting individual, disconnected snapshots, and towards something closer to a continuous, decade-long documentary of an active, constantly changing universe. One capable of catching a supernova the moment it ignites, an asteroid the moment it drifts into view, or a black hole flare the moment it erupts. Rather than discovering these events days, weeks, or sometimes years after the fact, Buried in a single photograph nobody happened to be looking at closely enough at the right moment. That's not a claim built around a single exaggerated headline. That's the honest, stated purpose behind an instrument 30 years in conception and a full decade in physical construction, one whose true scientific legacy won't be fully understood until its 10-year survey has actually run its full course. If this kind of story is what you come here for, one grounded in exactly what astronomers actually built and why, rather than exaggeration, hit subscribe and turn on notifications, because this decade-long story is genuinely just getting started. Drop a comment telling me what kind of cosmic event you think Rubin will catch first that no previous telescope ever could, and share this with someone who still thinks a single photograph can capture everything worth knowing about the universe.